Yeah, I can't do that.
That's supposed to be my squeakle sign, where it's like equal, like approximately equal.
Oh,
it's
they're
a
just like
squiggly equal sign, squeakles. So this is a non-repeating, even though it looks like 1828 repeats, it does not, in fact. It's infinitely long, non-repeating, irrational number. All right, and this is called the natural number. All right, so au natural number. All right. It's also sometimes called Euler's number. Euler's number. Because he was the dude that discovered it. And it's called the natural number because it shows up oftentimes in nature, oddly enough. Its ratios have it show up in nature in different capacities. And we actually will see this number primarily with exponential growth and logarithms and exponential decay. And it turns out that E, actually, should I talk about E before I talk about log base E? I probably should. It turns out if I wanted to figure out like compound interest, all right, there's a couple of interest formulas, simple interest and different things like that. But compound interest, one formula is A equals P times 1 plus R to the T, all right, where A is the final amount of your investment, P is the initial amount, R is the rate written as a decimal, and T is the number of years. So this is compound interest. So this is a formula for compound interest compounded annually. So compounded annually, where they calculate how much interest you earned once per year. Similarly, there's a formula for compound interest. A equals P times parentheses 1 plus R over N all to the NT, where this is a formula for calculating how much money you earned by compounding the interest N times per year. Let's see, why can't I not write pounded N times per year? All right, so for instance, if I wanted to calculate my interest at the end of every month, N would equal 12. If I wanted to calculate my interest daily, N could equal 365. If I wanted to calculate my interest quarterly, you could do it N would equal 4, right? Where it'd be every 3 months, different things like that. And what I mean by compounded interest is that not only would you earn, say, like 5% interest at the end of the year, in year 2, you would earn 5% of your original investment plus 5% on top of the interest that you earned the year before. And then the year after that, you would earn 5% on top of your original investment plus 5% on the interest you earned those 2 previous years before. So it turns out that your interest earns you interest. Okay? And I think I said the other day that Albert Einstein is quoted as saying that compound interest is the most powerful force in the universe because your money can just like start making you money like crazy mad fast. All right? And it turns out that with these in mind, right, you're able to like earn a lot of money. And some people earn so much money off of their interest that that's what they live off of. You don't have to work anymore. For instance, if you had like $1 million in the bank, I think, depending on the interest rate, you'd earn about $50,000 a year in interest, which is more money than I make per year right now. So if I had $1 million in the bank, I could just like, as long as I never touch that $1 million, it just keeps earning interest, and then I'd spend the interest, and then I'd earn interest, and then I'd spend the interest, right? And it wouldn't be all that bad. It would be a pretty good deal.
So basically, if I just borrow $1 million from someone and give it back after like 3 years,
yeah, something like that. But I imagine like if you borrowed it, like they'd probably want some interest back for the loan. I imagine. Actually, one time back when I had a credit card, I once overpaid my credit card, and then they wrote me a check like a month later for like the $1.17, and I wanted to be like, call them up and be like, hey, where's my like 29% interest rate on that $1.17 that I loaned you? But like, it doesn't work that way, whatever it was. Yeah, be careful with your credit cards, friends, because the bank isn't your friend when it loans you money. It's like, it's making a killing off of you some way or another. But anyways, compound interest, right? That's the idea. So that's n times per year. But what if the number of times you compounded per year, what if I calculated like n times where I wanted it compounding every second, right? So that would be a lot of time. What would that be? That'd be like 365 days, right? Times 24 hours, times 60 minutes per hour, times 60 seconds, and I would get 3153600 would be the value of n. So what was that? 31 million seconds, roughly, something like that, and then I'd be able to have, right, a value of n. But what if I wanted to calculate it per like millisecond? All right, so if I do that, I'll end up with like a little bit more money in the end. Or what if I just wanted to divide it up into like divide the year into infinitely many parts? All right, like infinitely many, where it's compounding continuously. All right, where like the formula would be doing the math so fast that it's immeasurable in the length of time that you're recalculating your interest all the time. And it turns out that's where one area where the natural number shows up, and A equals P times E to the RT. Apert is a formula for continuously compounded interest. Continuously compounded. So let's do a little example with this before we get too far, and then I think we might be able to get. Yeah, we'll see. We'll see what we got. So if I wanted to say, if I invest, let's say $1,000, blam, $1,000, at a rate of, let's say, 3.75%. And for a length of time that is 10 years, how much money would I have at the end of that time? So let's actually define some variables. So the P would equal 1,000. The rate would equal 0.0375. Because I have to write the percent in decimal form for this to calculate properly. And time would equal 10 years. So I'm looking for A, the ending amount of this. So I'd have 1,000 times E to the 0.03375 times 10. All right, so let's plug that in a Calculadora. Calculadora. So, you might be wondering, where is this E button on the calculator?
Well, I found it yesterday on my phone.
There you go. Yeah, what just happened exactly? So I'm doing 1,000 times E. Oh, come on, really? You call that in focus, camera? Come on. You disappoint me, computer. So it turns out log button is right here, and beneath it is the LN button. And you've got e to the x right there. So I'm going to do 1,000 times, and I'll hit second and this ln button, and I'll have e to the, all right? And now I'll just type in the, what was it, 0.00375 times 10, and making sure that that's all in the exponent.
8.0.
1, 0.
You have one.
Fine. Let's see, delete. All right, there we go. Okay, so now if I hit enter on this, I get 1454.99. So 1454.99. So not bad. Not bad at all. So clearly, if you're planning on making money off of interest, typically you'll not just make a one-time investment, but you'll keep adding to it. And there's an interesting thing where, how old are you guys? Around 16, 17? Yeah. Let's say you start investing $1,000 per year. Okay? $1,000 per year. Sounds like a lot of money, but you guys don't have a lot of bills usually at this point. And let's say you started at 16, all right? So you invest $1,000 per year, right? And then you put another $1,000, 17, 18, 19. And you do this all the way up until you're age 26, okay? So 10 years, you've invested $10,000 over that time, okay? And you've invested in an account where, probably investing in some sort of stock portfolio where you're earning, let's say about like 10% interest, okay? It turns out that by the time you retire, if you never invest another dollar in that account, you'll have roughly $1 million by the time you retire. Okay? So you invested $1,000 for 10 years. Whereas if I'm 30 years old now, but let's pretend I'm 26. We all know I look it. So good looking. That if I started investing $1,000 from age 26 all the way till I'm 65 at the same interest rate, okay, that I will barely catch up to you when I retire. Okay, so I would have to be investing for, like 39 years or something like that, and I would barely catch up to you. So I invested $39,000 and was left with $1 million. You invested $10,000 and had $1 million. So the factor that is the most valuable or effective variable to control is the time. All right? Time is the very powerful variable here. And the larger that variable in the exponent is, right, the more number of times this is compounded. So time is the variable that you have the most control over. So if you just suddenly made a decision, I'm going to start investing $1,000 per year until I'm 26 or 30 or whatever, you could have a lot of money by the time you retire. Whereas if I start doing it now, I'm already behind the 8 ball because I don't have as much time as you guys. It's too late for me to get a hold of this super big, great deal. And actually, because time is the most powerful variable, there's actually a proverb from the book of Proverbs, and this is something that some Jews will actually still take account of, where it says, a good man leaves an inheritance to his grandchildren, where I guess what sometimes they'll do is they'll skip a generation. They won't give the inheritance to their kids. They'll wait 2 generations before that inheritance pays out. And think about it, if you have 2 lifetimes of interest building on that, that's way more than just 1 lifetime and then spending it, and then 1 lifetime and then spending it. And you could actually have a far greater effect on your whole lineage and legacy as a result of having 2 lifetimes of interest building on top of whatever you're investing. So it's kind of interesting thing. And actually, I think I told you guys about my best friend who had died in Iraq a few months ago, right? Well, he didn't die. He died 6 years ago. I didn't tell that story? Oh. Okay, well, all right.
You're behind.
Yeah.
Wow, my apologies for not telling stories. But yeah, 6 years ago, my best friend had died in Iraq, and he had a life insurance policy. And his parents had taken it and created a foundation in his name, and I think it was $400,000. And so it gathers interest, and every year they give away the interest. All right, so they earn about $25,000 a year on that life insurance, or that life insurance money, which is now in an account earning interest. And as long as they only ever give away as scholarships and whatever, the interest, they'll always have a principal balance of that $400,000, and they could keep doing that continuously if they wanted. But they're interested in only kind of like having his name memorialized for about a lifetime. So their goal is that once, so they'll give away like $25,000 every year, or whatever the interest is, right, into scholarships, different kids from the same community that he grew up in. And then when they end up passing on, then I'm going to take over the foundation, and then we're going to start dipping into that principal is the plan, so that hopefully by the time I'm nearing the end of my life, we'll have brought that account down to zero and given away all of the money, and then his name, would have had, some positive, lasting effect on the community and society and people, for about what his lifetime would have been, assuming that it would have been about mine. So it's just kind of an interesting thing. Like, if you only ever give away the interest, you're never losing any money, and you're not having to earn that money. The money's earning itself. So interesting sort of situation there. So this is the first place where this E shows up, is in kind of sort of this exponential growth thing, or the first place for us where it's easiest to see it showing up. Now it turns out that there is log base E. All right, this is called the natural logarithm. And it turns out that log base E of anything can be written as ln of that. So ln as in logarithmic, or logarithm natural, or natural logarithm. All right. So it's just kind of a shorthand way. So your calculator speaks two languages as far as logarithm, or two modes, right? It speaks in base 10 and it speaks in base E. All right. So I think I showed you a moment ago that there is well, if I waited for it to clear up. Right below the log button is the base, or ln, which is the log base E, okay? And so this is the other type of log that we'll be using. So let's do some examples. So let's calculate what is ln of 3. Now question, is ln of 3, would you suspect that is bigger than 1 or less than 1? Well, what is E? This means 2.718281828, right? So this asks, what is E raised to that gives us 3? Now, E raised to the first power would give us itself, and 3 is bigger than itself, so this has to be bigger than 1, right? That would make sense. So it's always good to just kind of have that estimate. So let's figure out what is ln, let's see, is my calculator on? No. ln of 3. And I got ln of 3. You could close out parentheses if you're happy. And I get 1.0986 right there, 1.0986. Right? So that's how the ln button works. Log base E is what's implied by that. So you could also have, what is ln of E, actually? Now that I think about it. 1, right? That means E to what power is E? The first power. What would ln of 1 be? That looks like the absolute value of n, but that's not what that says. E to what power is 1? Yeah, the 0th power, right? Yeah. Actually, sometimes I'll end up writing ln this way, cap ln, because I feel like the L looks like a 1. But technically it is typically lowercase. Although on our calculator it's capitalized, but they actually capitalize a lot of their buttons. So I don't know if that's a stylistic choice or not. And it turns out not only is there ln, all right, log base E, but it turns out that there's also the anti-ln. All right. The anti-ln. All right. Anti-ln of, I guess I'll choose a different number this time. What would a good number be? Letter for a number. I'll just call it x. Anti-ln of x. So what do you think that would mean? What would the Right. What would the inverse of ln be?
X raised to E.
Close. This would be e raised to the x. All right. So ln is a logarithm of base e. So it was the inverse of an exponential function, right? And the inverse of an ln must then also be the exponential function. And actually, this is usually directly just called, like if I had y equals e to the x or something like that, that is called the exponential function. Like this is like a really cool function. Actually, man, someday when you guys take calculus, I'm telling you, you'll learn some crazy stuff about the number e. Like if I graphed, no, I won't spoil it. There's just some crazy stuff about e. The craziest. So anyways, if I wanted to calculate the anti-ln, I don't know if it should be lowercase or not, but whatever, anti-ln of 2, that is the same as e to the second. So if I wanted to do that, notice that the inverse is right above the ln button, right? And that's literally the e to the, so this means anti-ln of 2, okay? And I hit that, and I get 7.389, meaning that the ln of that, if I was to do it the other way, the ln of that answer should theoretically equal 2. All right, so 7.3891. 7.3891. So there's our anti-ln. All right. So this is called the natural logarithm. Let's see. So I did some exponential stuff. I'm tempted to do, well, we might get into solving those equations later. Yeah, we'll do that tomorrow. We'll just keep this a nice, easy lesson, I think. So I think I've covered everything I need to. I think you guys are going to be awesome for today. So log base e is an interesting number. And actually, someday, I will give you a formula that relates the number 0, the number 1, the number pi, the number I, and the number e, where each of those is used exactly once, and all of the most significant operations are used, and it is the most beautiful math formula ever. I'm telling you. Like, the 5 most important numbers are all related in a single formula, and it is incredible.
Do you have that like written on your wedding projector?
No, but I think I know of people that have a tattoo of this, even. But anyways,
That is embarrassing.
well, anyways. But anyways, Internet, that's everything we need to know about log base E, Loki, the trickster, right? Goodbye.